Well, they're playing the Jeopardy theme. Oh, shoot.
Does that mean it's 7 o'clock?
Yeah, I left my coffee in the microwave.
Okay, well, you've got about 2 minutes because I'm going to say hello to everyone first. Hello, everyone, and welcome to our class. We skipped last week, as you're all aware, but we'll just pick up with what we would have covered last week, which is Dan. These are our email addresses again, and we all welcome questions or emails on any ham radio related topic. Please, if you think of something or if there's something confusing in the book, send us a quick email, and we're glad to respond. And this is the dinosaur on the coffee cup, Mikhail. So it is therefore a funny coffee cup. This is being recorded, and actually all of our class session recordings are still up. Zoom hasn't sent me any nastygrams, so I'm leaving the recordings up as long as I can, but I may have to take the earlier recordings down, but we're recording tonight as well. And just a reminder, we're covering the questions on the exam in the same order they're printed in the textbook we recommend. And we also recommend this online resource. Tonight is our third class after we skipped a week, and tonight we're going to hear about skywave transmissions. We're getting into good stuff. This is poor Karen had to talk about FCC rules and regulations, but now we're actually getting into real radio. Dan is going to talk about why you can actually use a little tiny shortwave transmitter and just carry a signal sometimes all the way around the world. Gary, K6PDL, will show us some QSL cards, verifications of contact, a quaint ham radio custom. And then Dan will cover transmitters, specifically high frequency transmitters, actually how these radios work. This is really the interesting stuff. Next week, I get to talk about receivers. So before we get started, who has questions, comments, anything at all? Anyone with questions? Okay, you're all well informed. When you think of questions, and some of this material is getting a little technical and complicated if you haven't seen it before. So please remember, the point of a live class is that you can ask questions, and go ahead, try and stump us. We like it, and we're not afraid to say we don't know if we don't know the answer, and we'll try to find it out for you. Dan, that's all yours.
Oh, well, good evening, everyone out there in Radio Land. Yeah, tonight we're talking about ionosphere. Let me get the slides up here. Are you seeing a screen full of words?
Yes.
Lots of words.
Lots of words.
Good words.
You can ignore them. No. Let me try and minimize that and minimize that. And I had a lot of fun this evening trying to get PowerPoint to work. It would open, but it wouldn't display. So I was panicking for a while.
It's
There we
good
go.
practice for a real disaster if you panic now.
Yes. All right. So jumping right into it, the first question in the chapter has to do with the F2 region. Doesn't bother to explain what these regions are yet, but we'll get into that. But I'll just say the regions are labeled or named DE, F1, and F2, and sometimes F1 and F2 combined together. And fortunately, they are in order D being the closest to us and then F being the furthest away. So if you can imagine, well, just that the further your signal travels before it bounces back down, then the furthest layer is going to give you the longest region. Some more pictures. You know, just for fun, a lot of these pictures will also give you kilometers when unfortunately, all the questions in the test are in imperial units. So this is a little graphic, isn't really part of the test, but just showing you the different layers. You know, we're most interested in the troposphere, but we use the other layers for bouncing signals around. So as I mentioned, D is closest to the Earth, and it absorbs medium and high frequency signals. So medium is actually below what we've been talking about here in our class, although that we've gotten some new ham frequencies that are in the medium wave region. In the very beginning of radio, everybody was using the medium wave frequencies and thought the HF frequencies were just garbage because they really didn't travel very far. But again, the F2 is our go-to for long distance communications. But the D and E regions and F regions can be affected by the what time of day or night it is. So here's a very first question here that's very important. It's asking about the F2 hop. So this is one of those things where there's only two questions it asks you about the distance. So the F, you can associate the F2 with 2,500 miles, but then there's another question later on about the, I think it's the D, that's 1,200 miles. So fortunately, these are, if you just remember this, 1,200 and 2,500 miles. I'm sorry, what? 1,200 miles and 2,500 miles, and associate that with the 1,200 miles with the F2 region. You'll easily answer that question. So when the sun is overhead, the atmospheric layers at the maximum heights. The other answers on here are not even close to being correct. So it should be easy to remember that when the sun is overhead, the layers are at their maximum height. So critical angle, okay, we're getting to that. There's a question about critical angle. And so the angle that the energy from your antenna when you're transmitting hits the different layers will have a extreme effect on your success. So on this right-hand graph here, it shows the energy from the antenna coming off at different angles. And so a lot of times they want to design antennas so that they will have a low angle so that the energy will travel further before it bounces down. If it goes too high up, it will just become absorbed by the layers and not bounce. I think of this as like skipping a stone on a pond. You have to hit the stone just at the correct angle for it to bounce. Obviously, if you just drop it, it's not going to bounce. And again, it says that how well it reflects off the ionosphere has to do with the angle. So here we'll get into two terms, MUF and LUF. In this case, MUF stands for maximum usable frequency. Now on the test, they will also throw at you minimum usable frequency. But if you remember that you have LUF, which is the lowest frequency, then obviously that doesn't make any sense. So it must be maximum frequency. So the idea is that there's going to be a sweet spot between in frequencies that you could select of all of the frequencies that are available to you that will work at a given point in the day, if they're going to work at all. So we have the maximum and the minimum. So the lowest, below the lowest usable frequency, it says the energy is completely absorbed by the ionosphere. So then they have an idea that here, if your lowest frequency is above your max, oh boy. If your lowest frequency exceeds your maximum frequency, in other words, there's no window at all, then nothing is going to happen. There's not going to be any skywave communications. There still will be local communications, but their signal isn't going to be bouncing off the ionosphere. So here's just the opposite question. So if your frequency is between the maximum and the minimum, then they are bent back to the Earth. So this is a neat graph here. The right-hand graph again, that shows the lower in red and the upper in green. And so theoretically, communication, we will get this skipping off the ionosphere when your frequencies are between these two within this region. So if the red were to go above the green, or the green falls below the red, then nothing's going to happen. So right now it's 3 o'clock UTC, 300. So I would want to pick a frequency kind of in a narrow band here. And we do have a ham band at 18 megahertz. So theoretically that would work. You can see it sometimes we have many more frequencies available than others. And I assume that for where this is all had to have been calculated for 2 different points on the Earth. So wherever this was, you probably figure it out based on figure this out, but this is probably the daytime. This is probably daytime. This is probably evening, if I got this right. There's an app that you can get that will produce this kind of graphic. I used to have it on my phone for a long time. Never did anything with it, but it's kind of interesting to look at. Okay, so how do you determine if the frequency you're looking for is within this, with a practical way to determine rather than just a calculation? So there's a thing called beacons. So there's 6 beacon frequencies that are placed all over the Earth. And if you can hear, say, one of the beacons, we're here on the West Coast, and if I could hear 4x6 to you on 14 megahertz, there's a good chance that I'll be able to work this part of the world. If you can't hear anything, then the bands just aren't open. So here, the question here on the test is associates maximum usable frequency with international beacons. This one here, by the way, I think is the UN building. Another way, a more modern way, is to use something called WSPR. That's what Weak Signal Propagation Reporter acronym. We usually pronounce it as WSPR, which is kind of nice because you're looking for weak signals, which will come in as at a WSPR. Oh, here it is. So that's a method where you transmit and you can look at a website and it will tell you what stations have heard your frequency. So it's just the opposite of a beacon. You're not listening, you're transmitting, and the other stations report that they've heard you. And the converse is true. You're reporting to the internet what stations you heard. And so you come up with this really nice graphic of all of the stations that have heard you. I was going to show that, but I thought it might take up a bit of time, so I just skipped it. It's the only question on there, just to remember that weak signal propagation report. The other options on that question you might have heard from last week, they're Livia, PSK31, single sideband, SSB.SC, which I don't know what SC stands for. But again, if you can remember WSPR and associate that with low frequencies. So again, this is a little fine point on this lower and upper usable frequency. So it's saying that the best frequency to pick would be one just below the maximum usable frequency. That's going to give you what the book calls the lowest attenuation, so the least amount of signal fading. And of course, the maximum usable frequency is, oh my, it said all choices are correct. It's of course mostly on solar radiation and ionospheric disturbances, but also time of day and path. So this is an all of the above question. So here we go. It was the E region, not the D region. Of course, remember the D region likes to absorb signals. So this one is the E region maximum hop is 1,200 miles, which fortunately is half of the F region. 1,200 miles is an option on this question, so we'll have to just remember again the E with 1,200 and the F with 2,500. Want to, that's something you could write down on your scratch paper before you even start the test. And here's what it would be if you were looking at it in kilometers. So as we mentioned before, the D layer is closest to the Earth. So that's kind of an easy question to answer. They give you DE, F1, and F2 for answers, and then just remember that the layers start with the D and it being closest to the Earth. This is pointing out that the altitudes actually change a little bit during the winter and summer, or day and night. So none of this, of course, is absolute. You know, it's like, oh, my signal went 2,600 miles. Well, yeah, of course.
Dan? Where does the D layer go at night?
It goes to bed. No. No, this has to do with the how to explain that.
If it's irrelevant, go ahead and skip it. The more I read
No.
about this stuff, the more physics questions come up, and
Oh, I
I
know.
confuse
Well,
myself.
and so much of this is a oversimplification of something that's extremely complicated. And did
When
I
this-
hear?
When the sun hits it, it becomes agitated and active and will carry signals. But at night, when it's on the shadow side of the Earth, then there's nothing to activate, to generate the bounce effect.
Okay, so at nighttime it's cold enough that the signals will congeal into something usable.
Now, the D layer works during the day. Have I got that right, Dan?
Yeah.
Yeah. At night, it disappears because it's on the shadow side. It needs the solar wind to hit it. But the Earth is blocking the solar wind from hitting the D layer.
Oh, okay. So
at
it's
night.
in the Earth's shadow in between.
Correct.
Got it.
Yeah.
Got
That's
it.
why.
Here's it showing the day producing the D waves, and then the F1 and F2 separating. This is showing you how that, based on how far you would like to talk, or that you can talk, may change between day and night. You probably have, I don't know if anybody is my first experience with radio was listening to AM radio. And of course, the AM radio signal travels much further in the nighttime, and that would be slightly below the 160 band. So in the daytime, it's more regional. In the night, it can travel much further distances, and that's why we would have some stations that would have to lower their power. In fact, I think now KSCO would, I think, lower their power and change their pattern at nighttime so as not to interfere with another station that might have been a clear channel station. I still remember how excited I was that I heard KDKA over in Pittsburgh, in the middle of the night. And these upper frequencies, these upper bands, 15, 12, and 10, are going to be more local. If it's going to be very rare, although lately it's happened occasionally when we have brief openings in the daytime on 10 meters. And then here again, it says the D layer is the most absorbing. Okay. Most absorbent of the long skip signals during the daytime on the frequencies below 10 megahertz. A lot of these questions, as usual, are stating the same thing in many different ways. So these are the lower frequencies and are more difficult during the day because of the delay of absorbing the signals.
Use more difficult, but it does. You can use those bands during the day. It's just rare, or
Yeah,
it's really highly unlikely. It's not worth the time.
yeah. For every statement, every absolute statement here has a time when that will be wrong, and that's the great thing about the amateur radio is it's really all of this information about these radio propagation is not terribly old. I mean 100 years compared to what we know about, say, the way light works, and we still don't know. Really don't know is everything there is to know about. People are still learning things. Then there's a question about atmospheric noise. Again, on the lower frequencies during the summer, and that's just nature. Of course, these days, a lot of the static is going to be coming from human-made sources, but then they talk about scatter propagation. Scatter propagation is a little easy, I think is easier to understand because if you think about if you shined a laser pointer at a mirror, the light would bounce off the mirror and you'd see this very bright spot across the room at the same angle that of exit that it was incident. But you'd still see that dot of red from the laser pointer in the mirror, although it'd be extremely dim compared to the actual power of the laser. And that's sort of what's happening here, is that it's skipping off the ionosphere, but there's some of it that gets reflected back, and as it doesn't hit, unlike the laser pointer example, it does not come straight back at the station. I'm looking for something here. Okay, so yeah. So they're also distorted because of the way the energy is coming back. It comes back, as this is showing here, different paths. So if you're in this area listening to the signal, it'll be very distorted. I think I've heard this. Once I saw this, I kind of explained to me something I'd heard on AM broadcasting quite a bit. Even for local stations, you should think that it were extremely strong, but there would be this seemingly energy coming back and canceling the local energy out, but not in a very I don't want to say, well, predictable to my ignorance method, but I think now it's actually hearing backscatter. So here it is. A characteristic of these scatter signals is they have a wavering or fluttering sound. That describes what I was hearing. So this question is talking about an azimuthal projection map. So the map that we're all familiar with distorts the actual shape of the continents to make it fit a round sphere fit on a flat page. We probably all know that. So if we were trying to really have a really understanding of what is north of us or what is east of us, we need to look at it as an azimuthal map. The map that they give you here, I don't think is of much use because these distances aren't all that far away to show the distortion. So I put in this, then they put in this question here. We have to take a little detour. So there's a concept of long path, which is just totally blows my mind. The idea that you could be transmitting, say you had a beam and you could transmit in one direction, you actually could hear yourself coming back delayed because your signal bounced around and traveled all the way back around, all the way around the earth to come back to you. It's just like, that just totally seems mind-blowing to me. So the answer here they're talking about, though, is that long path would be slightly delayed. Well, yeah, because even though it's traveling about at the speed of light, it still takes a little bit to travel all the way around the Earth because it's bouncing off the ground, bouncing off the ionosphere. It's the, I guess it's the billiards equivalent of bouncing the ball off of all of the surfaces to come right back to where you were. So this is a map that I put in centered around the, well, close to the western part of the United States, and you start to see that things aren't where you think they are. Europe is not east of us. It's more north of us. And this, when I first time I saw this, it explained a great mystery to me that one field day, as a new ham, was my first field day. I was operating on the 20 meters, and our antenna was of course pointed east because we wanted to talk to people in the United States. But somebody came back to me from South Africa, and I thought that was amazing because South Africa is not east of us. Well, yeah, it sort of is. It's more east of us than any other direction. So that's where this map would be useful. If you had a tunable antenna, you would be useful to know which way to point your antenna if you wanted to talk to somebody, you know. So then there's the concept of short path, which is short path is the direct path between two stations, and then a long path being the opposite, where the long path would have to go all the way around the Earth. And here, this next question is just associating the fact that higher sunspot level equates better likelihood of long distance communication at the higher frequencies. So we're just coming out of a period of low sunspot activity, and so I'm hoping this will be a good season for sunspots coming up in the following years. You know, the greatest one we had in my lifetime was in our lifetimes was in the mid 70s, which is really the main reason why the CB hobby went wild, is because you could, in fact, this is exactly what happened. Is I was at sunset, which will be an important question later, driving down the street at sunset with a perfectly legal installation in my car, talking to somebody in New Orleans on 3 watts. But the sunspots were just crazy. So the maximum usable frequency was obviously above the 11 meter band, which is around 27 megahertz. So if I was a ham operator, I would have been able to operate on 10 meters and probably talk around the world. So the sunspot is a long-term phenomenon, but what they want to point out here in this question is that it actually has a 28-day cycle based on the sun's rotation. That kind of makes sense. The sunspots aren't going to be uniform throughout its entire circumference. So as it rotates, it's going to change the cycle. And some pictures of sunspots. Oh, solar flares, sorry. So here, this is another thing. Seemingly, we can bounce frequencies, bounce our energy off of just about anything. And so even the aurora will allow us to bounce VHF frequencies off of it. So this question says, what benefit can high geomagnetic activity have on radio communications? So you have to associate, again, geomagnetic activity with auroras. The other questions don't mention auroras at all. And this is stating it again, that the least reliable for long distance communication during low solar activity are the upper frequencies. So the maximum usable frequency will be below these 3 bands, or one or more of these 3 bands. So this is part of the explanation, as I understand it, why the new hams are limited to the upper frequencies by and large. It didn't used to be that technicians had any privileges on the 10 meters. or below. But that was kind of a recent addition. But I think the idea was that, okay, you're New Ham. We don't want you talking to just, anybody all over the world like you could on a lower frequency. So we'll limit you to these upper frequencies that tend to, where the energy basically just goes into space. It doesn't bounce back down. Of course, nowadays that's, with social media, that's just a laughable concept that you would try and limit somebody's social interaction with people in other countries. So, I think this whole notion of keeping New Hams off of the lower frequencies is probably is pretty dated. But that's just my opinion. Okay, now solar flux index. Solar flux index is a measure of solar radiation at 10.7 centimeters, which is 2,800 megahertz. This is one of those questions that are probably not of much use to you. But these measurement produced by, it says in Ottawa, Canada. So it gives you a K index, which is a number that is a figure of merit that shows the stability. So a low number is it would be a good number. So, so in this graph, it shows the yellow hitting 4, indicating at least likely of being able to use this frequencies. So the questions, on the solar flux index, the only answer that has the 10.7 centimeters in it, there's only one that has the 10.7 centimeters. So if you can remember the solar flux, and again, in 10.7 centimeters, you'll find the right answer. The same thing with K index. It's the only answer that I see that has a short-term stability in the answer. So you're gonna have to try and remember to associate those two things, that it's a short-term stability. And then they have an A index, which is long-term stability. And again, in the answer, there's the only answer in that question that has long-term stability in it, associated with the A index. So if you can remember, K is short-term and A is long-term, you'll come across the right answer. To me, these are really esoteric. And that's why I'm just trying to, focus on getting the right answers. And then if you're really interested in this later, you can really delve into it.
Would you actually use these if you're thinking about getting on the air and trying to decide what frequencies to start to listen to for the evening? Would you go to those indexes, or are they just there for effect?
There are I've heard people talking about this kind of thing on the repeaters that are really into HF and contesting and everything. But like I said, it's just pretty esoteric. And the thing is that, as hard as we try to predict what frequencies are going to work, there's always those times where that just, it's like, I should be able to talk to Europe right now, and it doesn't work. Or just the opposite happens, You can't talk to Europe, but you can hear your own speech coming back to you. So it takes 8 minutes Takes 8 minutes for the ultraviolet X-rays from the solar flares to affect the radio propagation. And these two are associated with together with solar flares affect the magnetosphere and cause a temporary disturbance. There's a question on here, maybe not. Oh, okay. It's the ultraviolet, of course, travels at the speed of light, which takes 8 minutes. It's the other thing that the sunspot activity can take up to 3 days to affect communication. So this question here, the critical part of this question is the 8 minutes. It's actually the shortest period of time too. If I was looking at this and looking at these answers, I'd go, wow, these other ones are really way too long. Even 1 to 2 hours seems a long time for anything to ultraviolet light coming from the sun to the earth. If you wanted to, you could sit down and calculate the speed of light from the earth to the sun, or just remember 8 minutes. Oh no, SID doesn't stand for sudden, oh no. Sudden ionospheric disturbance on the daytime isospheric propagation of HF frequencies. Disrupts the lower frequencies more than the higher frequencies. So the idea is that this can make the bands become so noisy that it's pretty hard to use any skywaves. So in this one, in this question, again, super esoteric question, the answer that talks about disrupts the lower frequencies is the one to look for. You know, I think if you look at a phenomenon has the word disturbance in it, it's probably not going to enhance the propagation, which is one of the answers. So this is showing that showing two things in this graph, how if the lowest usable frequency exceeds the maximum usable frequency, for that period of time, there's not going to be any skywave propagation. But fortunately, it's temporary. In the book, it's got a graph talking about the K and the A indexes again. So just remember that SID has to do with a brief interruption in the skywave. You might have heard this last few years. We've seen this in the news where we're talking about geomagnetic storms that geomagnetic storms that have you know, they said, oh, it's going to hit the earth in a couple of days, and it could be interrupted communications, and that's what this is talking about, degrading the high latitude HF propagation. So here's that thing I was looking at where it says 20 to 40 hours for charged particles from a coronal mass ejection to affect radio frequency. So it's much, much longer than the 8 minutes. But in the answers in the book, it does include an answer that is 4 to 8 minutes, but that's the wrong answer. And the only other one that is in hours is the correct answer. The other two are in days. And again, this can actually affect more than just HF frequencies. On here, they mention it takes 20 to 40 hours instead of the usual 8 minutes. This is a repetition. So this looks like the same text, but the actual text from the book is how are radio communications usually affected by the charged particles. And the answer is that the HF communications are disturbed. So the 20-meter band is usually the go-to band during the daytime hours. Just like it is the most reliable band during the daytime. Okay, we'll take a break and hear from
Thank you.
Gary for a minute about
If I can get my mic unmuted. Yeah, this is just a short brag on my part of my QSL cards, some of my QSL cards. I've been, a lot of the cards I got were when the sunspots were good, when I first got my license 10 years ago, when the sunspots were at a peak and just about to head down to the current low. And I got some nice contacts that I made at that time on voice. And during the lean years, then I get on digital modes and I make some contacts. See if I can get my screen up here. There we go. Everybody see that? Is that up?
yes.
Oh, okay. QSL cards have been around for a long time. They were used to tell another station that I heard you and what your strength was. Here's one from Channel Islands in England. And they received a signal from, I can't see it now. I think it was a school in Indiana. Oh, here's the School of Engineering in Milwaukee. And they got a card. They sent a card to this person in Alaska. And they were real happy to get that contact from. And this is all CW with a simple oscillator to transmit on and a simple detector to listen. Now, the information on there, this is a fictitious contact I made with Karen, and it has the person's call sign, day, month, year, time, frequency, and then an RST report. We covered that a couple of weeks ago with the readability, signal strength, and tone for Morse code. But in this case, the signal was perfectly readable for a 5. And the 9, where's that come from? Well, signal strength, very strong. You have a meter on your radio that goes from S to S9 and then overdriving. So a 5/9 signal would be a nice clean signal at basically peak power, because beyond this, the signal just degrades and it gets noisy and messes up the front end of your radio. And one of the points of QSL cards is to get wallpaper. And this is one of my Worked All States awards for digital. And it's on 4 bands. And I also have added 17 meters to this, but I don't have the sticker yet. And working around the world, you have the DX Sensory Club, DXCC, as it's called. And that's for working 100 countries and confirm contacts with QSLs, either on the logbook of the world, which is electronic logbook, and electronic QSL, or in actual paper QSL. I think next is my QSL card again. That's my current one. I think we just saw that. This is my current one. And my logbook prints out a mailing label. And that mailing label just happens to fit right in this little block. So all the contact information is pre-printed for me on a label that I can just slap on my card to mail, which makes it real handy and real easy. Here's the card I got from GB2NZ, needless to say. And it's one of the styles of cards for commemorating events, special events. And there's all kinds of special events. Next one here is celebrating George Washington and the troops running through this town, or coming through this town, where they were able to rest without fear of surprise attack. On the other side of the card is the picture of the inn that they stayed at. And then a couple of months later, the same guy on the air, and he's celebrating the Liberty Bell, which had been whisked into hiding from Philadelphia along the same road. And the other side of this card is such. And the neat thing about these is when you put them side by side, they create a larger picture. So these are kind of fun to collect too. Route 66 occurs every year. There's 12 stations that set up along Route 66 from Los Angeles to Chicago, or maybe St. Louis. I'm not sure. I think it's St. Louis. And I've managed to work as many as 10 in a given year. And there's always a couple that are real hard to get, but these cards on the opposite side, when you lay them out, form one large QSL card also. And then here's all the stations along Route 66, the call letters and the location of the stations. Oh, it does go to Chicago. There we go. This card is from a station, a research station up in Canada. It's in way up inside the Arctic Circle, and it's about 90 miles from the North Pole. And I happened to get this guy. I took the coordinates and looked to see where it was on the map, and by golly, can't get too much further north than that. And we were talking about 10 meters. These are all voice contacts that I made on 10 meters. And you, even with a technician license, you can get on HF and make some nice contacts. And I'll just shoot through some of the other cards that I've got. This one here is interesting. This contact in England, I was using a program called Grid Tracker. And what it does is it takes and follows my signal and reports back all the people that are hearing me. So here's the map that it produced. And here I am here, of course. And here's the British station over here. And there's a nice blue arc line along here to shows, the path that it went. But notice something else. We got daylight, we have night. Oh, back up. Day and night, and there's our gray line. And notice how the signal path just follows right along the gray line. So at dawn and dusk, it's kind of a magic time to get on the air and make contacts, because your signal just travels right along as the layers are switching. And now field day, where we get on and do satellite contacts and talk to satellites and try to get as many satellite contacts as we can during the year, or during the field day event. This is our setup up at Ben Lomond Training Camp. This was a horse trailer, and we set up in the horse trailer, and we kind of had demonstrations and displays around for people to to educate people on how satellites work. And we had a lucky streak. We managed to make contact with this guy here. Reed, I can't think of his last name. Anyway, Reed was here on the space station, and that was a whole lot of fun. So I got a signed card for the ISS, and there's one of the number of other types of cards you can get. This one, notice the call sign HA3FOK. This is a Hungarian call sign, and the radio operator is on this freighter, and he travels from Japan to Hungary through the Panama Canal. And I've worked him 3 or 4 times. And in this case, he's right here in this square northwest of Hawaii. And it's kind of fun. As I travel, I caught him here again off the coast of Baja. And I also caught him, I can't see because I've got my image blocking our images. Oh, here we go. Off the coast of Mexico, near Mexico City.
Hey, Gary,
Yes.
can you go back a slide, please, to the QSL card?
Yeah, hang on, let me.
Can you explain the report there for this QSL card? It doesn't look consistent.
Okay, so he's confirming contact with me on July 7th, 2018, at 38 minutes after, or 38 minutes UTC, Zulu time, which would be July, that'd be 7 hours difference. So it's about 4 in the afternoon, 4:38 in the afternoon. We were on the 20-meter band, working FT8. Now the signal report on FT8 doesn't go by RST, readability and signal strength. What it does is he sends me a signal how far below the noise level he picked me up. So in this case, he picked me up at minus 13 decibels below the noise level. So if you turn the volume up and listen to the noise on the radio, you're not going to hear a signal or hear my signal. It's just noise. But the WSJT software, the FT8 software will pull this weak signal and go, it's kind of like the way Whisper works, same idea, and pulls it, signals from below the noise level up, and you can make a contact. And in the locator is a grid tracking system. I live in grid CM97. Dan, I think, lives in CM86, 87. Right, Dan?
That sounds right. Yeah.
Yeah. Well, this was DK87, which was, I believe, off the coast of Mexico. Yes, it's off the coast of Mexico. So that's what all this one, that's all how this all reads out.
And that's
And-
why the squares on your map are not points,
No, they're
because they're a grid square.
right.
Gary, I missed your introduction. Is this a postcard?
It's a postcard size, and through the history of ham radio and even broadcast radios, if you were listening to Dan, probably could have sent a letter off saying, hey, I heard you in Philadelphia, and he would have gotten a QSL card back from the broadcast station there in Philadelphia. Yeah, go ahead.
Is that just something where they put your name and address and a stamp on it and put it in the post, and that's how it gets to you?
Well, we don't do that anymore. In fact, when this, let me.
Or
when
do
I
they
finish-
email them, I guess?
Well, no. Well, they do have email QSLs, but that's really cheap. You know, I like to have the actual paper QSL. You know, like, well, that's mine, but I like the actual paper QSLs. And I don't know if you can see my screen well enough. No? Oh, you can't. I know you can't. My wife is on a
If you stop sharing, Gary, we can see your video full size.
Okay, I'll do that. Stop share. There we go. Okay. So I have a card with my address on it, and I'm going to send this envelope to the person that I'm making contact with. I take my QSL card, and I can't see what I'm doing here. I lay it on the flap of the envelope, and if it's international, include $2 or $3 to cover their postage, and put that behind so it can't be seen through the envelope. And then when you put it in the envelope, the seam side, the flap goes down. That way, when they cut it open, they're not going to cut open the flap on your envelope. It's a little trick that I learned the hard way, but it's guaranteed me getting more cards, by doing it that way. I think I just have a couple more cards to show, so I'm going to pop back into sharing mode. Here we go. A couple more cards that I've received. Okay, here's my South Africa. That was exciting. I'd never thought that I could get that far. That was, I think, 12,000 miles to South Africa, 10 or 12,000 miles, but that was a nice hop. And it's not advancing me. Thailand, I have a friend that lives in Thailand. He's an American friend that I've been trying to talk into getting a ham license since I got mine, and we were both into CB. And when I got this card, I sent him a picture of it to say, hey, look, I can actually make a contact with Thailand, so get your license, which he hasn't. But in Morocco is the other side of the Morocco card. And the Galapagos. I love this one. And Kazakhstan, that one came out of the blue. And when I heard him, and that may be almost as far as South Africa. Seems closer, but it's almost as far. And Che Guevara, Cuba. And that's it. That's it. Any questions?
So how does the ARRL get involved with exchanging QSL cards?
Well, they have Logbook of the World. And I didn't really want to get into that because that could be an hour talk on just getting Log of the World set up. But basically, I send my log to the ARRL, and the stations I'm working send their logs to ARRL. They compare them. They say, oh, you got a match. And there's your QSL. So most of the contacts I have for my worked all states, and most of the contacts I have for the DXCC, the 100 countries, were logged on Logbook of the World. But I had like 92 countries on Logbook of the World, and I had 8 more cards that I could finish it up and get the DXCC. So I took them to Pacificon, and they were checked by a card checker at Pacificon, and I got credit for those 8 cards by he gave me credit for those cards. Larry, you had something? Oh, sorry, that was my cursor on the screen. Any other questions?
Yeah. How much of this is digital and how much of it is a voice?
During the lowest peak or lowest time of the sunspot activity, I was using digital predominantly, strictly. And I got DXCC on 5 bands in digital mode. But they have DXCCs for voice voice modes. They also have DXCC for CW. So you can get 3 DXCCs, or you can get, what do they call it? I've had a rough couple weeks. I'm not thinking clearly. But in my case, what I was working 10 years ago, and I'm going to start working more sideband because the bands have improved. So the solar flux index, you hear that one? The higher the solar flux index, the better chance you have of making a contact on long distances with voice. And it still works on the digital. You can still make long distance contacts, but so many people can make a contact that it gets really crowded and noisy. So it's like shooting fish in a barrel, but it's nice to get the voice contacts. I'm kind of rambling, so I'm gonna turn it back over to Dan.
So you guys will be getting your general license at a really good time if you're interested in this traditional shortwave aspect of ham radio, because for the next 5.5 years, conditions are going to be getting better and better and better as we move into this next cycle of sunspots. So things will be improving month to month and year to year. It's a great time to be started in the hobby. Dan, how do radio transmitters work?
I'm talking to myself again. I said, I have no idea, but let's see if we can figure it out. We're getting from the ethereal to the concrete here. Okay. There we go. So now we're talking about HF transmitters. This first question is, I think we've talked about this quite a bit, or a little bit. It talks about amplitude modulation. So I think it's been brought up before that we start out with a transmitter that's producing just pure energy, pure RF energy. If you hook that up to a antenna, somebody might hear you, but all they'll hear is just a constant signal. So there's no information imparted on that. The simplest way to impart information is by turning the signal on and off. And by doing that in some reasonable method, we can communicate through in what has become Morse code. And turning that continuous wave transmitter on and off, we produce what we call CW, the continuous wave. Probably, I think the next simplest thing to do is just change the amplitude of the signal, how much energy we're transmitting, say between 0 and 100 watts, in proportionate to the frequency and amplitude of speech. And that's what we call amplitude modulation. So the question is, what type of modulation varies the instantaneous power of RF signal? And I think if you think about, well, I'm changing the power level, isn't that changing the amplitude? The other three are legitimate modulation schemes, but they are has nothing to do with the power level. So a fairly easy question to one that is useful if you ever wanted to actually build a transmitter, which few of us ever do anymore. This is talking about a balanced modulator. So the idea is that you're combining two signals together to create again, a signal that has information on it. And so the question is, what circuit is used to combine signals? There's no way in English to associate, I think, balanced modulation with combining signals, except that, again, you're trying to impart information by modulating your signal. So maybe you can associate those two together. There's a little circuit on the right side, which probably means absolutely nothing to most of us. But it is showing how it is combining two signal sources to get a third signal. Here's just another way of drawing it. So when you add two signals together, or add is not really the correct term, but when you combine two signals together, you get more than just the sum of the two frequencies. And so you need filters to filter out whether you want upper sideband or lower sideband. If you want AM, then you don't need to filter out sidebands. Another way of describing AM is a double sideband signal, which is not on the test. And so here we go. A filter is used to process the signals from the balance modulator and send them to the mixer. So in the question, the answer is filter. So phone emission that is the narrowest bandwidth is a sideband. So AM, like I said, is double sideband. So single sideband is cutting off one of the sidebands. And not only does it free up that space, it also has some other benefits. It's just a more efficient way of communicating. But the answer is in the question is single sideband. And here's again a transmitter block diagram, which doesn't really help answer this question at all. So here it talks about speech processing. Now, we've got, let me go back to this one. So we've got a microphone, a mic amp, sending a signal into this balance modulator. So this signal, of course, is fixed in frequency and amplitude and is rock solid, but of course your speech can be all over the place. And so this amp will probably not only do some frequency limitations, so we're not transmitting unnecessary frequencies to keep the bandwidth down, but it also will ideally process the speech to increase the intelligibility. And what that means is by applying some automatic gain control to your speech. It's critical to not send too much speech energy into that circuit, or you will be transmitting, transmitting energy that's just not in the, just not optimal. You can produce out of it just produces noise. Whoops. How did I get here? Okay. So the other thing about the speech processor is it'll also boost your quieter parts of speech, so it'll make it sound louder. So here it says in this answer, the speech processor increases the average power. So the idea is keeps the speech within a narrow limits of amplitude. So on some radios, there is this speech adjustment this automatic level control can be adjusted, and some it's just automatic. There isn't really an adjustment, or it'll be an on-off switch. So so the answer to that question is the transmit audio or microphone gain. So if it's not, okay, here we go into a digital mode. So if you're transmitting audio frequency shift keying and your ASL is not set right, what will happen? Well, the signal would distort and cause spurious emissions. Spurious emissions means emissions that are not within the proper envelope of the signal. And again, that's another question. It's the same version of the same question, is that the ALC is to reduce distortion. The spurious emission is a type of distortion, but here we're just talk about distortion caused by clipping your audio. A lot of the digital modes, like AF/SK, or almost all the digital modes, are actually more critical for the levels than for speech. And that kind of makes sense, because we're used to hearing and compensating for different amplitudes and other, I sound right now much worse in over this Zoom call than I do in person, which is, if that's possible. Yet I hope that you can understand what I'm saying. In a digital modes, that the digital modes aren't that smart. They need to be set more precisely. Some of them not only in level, but also in frequency. The frequency has to be extremely tight. So it is possible, probably not with a modern transmitter, but it is possible that you overdrive with this ALC. You can actually damage your components. You think about a radio, it's making some assumptions in the design about how robust the components can be. And so, they don't necessarily design a transmitter to operate under the absolute worst conditions. So it is possible to damage a radio, and it is important to not overmodulate. The other thing, it's always best to not, if you don't have to even operate your transmitter at maximum output. If you have a 100-watt amplifier and you turn it down to 90 watts, nobody's going to probably hear the difference. So an incorrectly adjusted speech processor can cause distorted speech splatter and excessive noise pickup. I think that's pretty clear. So you're just basically trying to shove too much speech into that poor circuit. So flat topping, again, is another type of distortion, which we would, in audio terms, call it clipping, where the excessive drive, you can't drive the signal more than 100%, so it starts to flatten the top of the signal and starting to turn it more into a square wave than a sine wave. And that would produce a lot of harmonic distortion. Make a lot of people unhappy on the bands. Yeah, here's a picture of clipping, or flat topping as it's called. This is kind of funny when I read this. It says, one test that is often run on a sideband transmitter is a two-tone test. Two-tone test analyzes the linearity of the transmitter. So this is a common test on many different amplifiers, both audio and RF, because two tones will produce these combinations of additions and subtractions of the two signals. So you'll get A plus B, you'll get an AB, you'll get an A minus B, sort of combinations. And if the transmitter isn't linear, you'll start to get non-harmonically related signals. But it kind of cracked me up about often run. It's maybe often run by the manufacturer, but I don't, or somebody that's trying to repair a transmitter, but I don't think that's commonly done by the user.
Dan, where it
Mhm.
says distortion, is that an example of flat topping?
Yes, here, yeah. It's
Okay.
by, it's flat topping the both.
Yeah, I just didn't know if it was the same phenomenon that it described, or if
Exactly.
it's kind
No,
of hard
it
to
is.
tell from the book.
Yeah, and if you think about it, well, what happens is that when this signal transitions so abruptly, it is where the distortion occurs. Okay, changing subjects here. What is this, a modulation envelope of an AM signal? So here we're talking about you have a high frequency, say it's a megahertz, that is modulated by, say, 1 kilohertz. You've got you can see the low frequency represented here as the way the high frequency is modulated. And then so we call this whole thing the envelope. The waveform, what is a modulation envelope of an AM signal? The waveform created by connecting the peak values of the modulated signal. So they're just saying if you draw a line connecting the peak values, you'll see the envelope. And an oscilloscope is a piece of a test equipment that would show you that. In this example, it's just showing you a square wave and a sine wave. It's not showing you the envelope though. Yeah, this is a similar question here. Oscilloscope is a piece of test equipment that contains the horizontal and vertical channel amplifiers. I think this is the only question that is like this. That's talking at the question is test equipment containing vertical and horizontal amplifiers. And it lists 3 other actual pieces of test equipment, but the oscilloscope is, of course, the correct answer. And I think this is the only question like it. So if you can just, again, associate horizontal and vertical channel amplifiers with oscilloscopes, you'll be good to go. It's just showing you a old-fashioned oscilloscope. which in a sense is a television in a way that's just producing time versus amplitude. It's funny, we were talking just earlier this week about a particular really popular oscilloscope from the 70s. We, John and I used quite a lot and had a bit of nostalgia about. These days, there's a picture in the book of a modern digital oscilloscope that's much smaller and boy, I sure wish I had when I was doing field service work. So the oscilloscope is the best instrument to use for checking the waveform of a CW transmitter. So even though we talk about CW in terms of on and off, we don't actually want to turn the transmitter on and off because you end up with this, you would end up with something that it looks more like a square wave. And a significant thing about a square wave is it will produce an infinite amount of harmonics. That is something we don't want. So we actually have a rise time and a decay time to the time envelope of your CW signal. And so you can measure that with an oscilloscope, especially one that is can capture the signal. And so like in reviews in QST magazine of transmitters, they will publish these rise and fall times. If it's too short, too fast a rise time, the signal will sound, was described to be chirpy. And so you'll get people complaining about your chirpy signal. Yeah, it's just amazing well, yeah, it's almost 50 years. It better have been some technological improvements, but oscilloscopes have gotten, of course, smaller, better, and cheaper. Oscilloscope used to be one of those things that no hobbyists owned, except used and out of date. So if you're going to hook your transmitter up to an oscilloscope, you're certainly not going to blast 100 watts into the poor thing. So you need an RF attenuator to hook it up to the transmitter. So we talked about dummy loads before. This would be basically a dummy load that has a connection to the oscilloscope that has a lot of resistance in series with it. So the answer to the question talks about a RF, attenuated RF signal output to the transmitter. So the thing about a digital voltmeter is very nice. We can all afford one, but they will not show you waveforms. Some of them will tell you the frequency of a waveform that you're giving it. It even may correctly tell you the amplitude of the waveform, but you cannot see what the waveform looks like, and that's where an oscilloscope. So this answer about complex waveforms can be measured. Well, it's almost waveforms at all. And in the answer, it looks like waveforms is the only correct answer. So again, if you associate waveforms with oscilloscope, so oscilloscope is used to look at waveforms, you'll be right on the money. So if you look at this, you want to know what the amplitude of the first wave is versus the 10th wave. You're certainly not going to do that with a digital voltmeter. So again, when you're talking about transmitter keying, you would also think that, again, that's something that would happen instantaneous. But because your transmitter, well, more specifically, your transceiver, because there's a receiver and a transmitter in one box, you're going to need to give the circuitry time to transition from receiving to transmitting. And so there is actually going to be some delay between the time you key down with your key before it actually starts to transmit. And so the answer is, again, to allow time for the transmitter receive changeover. And again, it's the only answer that mentions a receiver, which is what this whole thing is about, to give the transmit receive changeover time. Oh, here's something that absolutely nobody needs to know. I'm sorry. Some of these questions, as I mentioned before, are just so esoteric. So if you look at this and go, why the heck would I ever need to know this? It's just on the test. It's an important subject, but unless you're designing transmitters, you're just not going to need to know this. So the idea here is that that a transmitter, I'll say, when you build a transmitter circuitry, it is possible to build one that will self-oscillate, even without whatever crystal or whatever electronic circuitry or oscillator you're putting into it. In fact, I did this once. I joke that the first transmitter I ever made was transmitted on TV channel 2 video channel. What I had done was to build an audio amplifier, and I somehow messed it up, and it went into self-oscillation. And the only way I knew that was two things were happening. The transistors were getting hot, and channel 2 across the room was the picture was all screwed up. So I was like, oh, great. Wanted to make an audio amplifier. Instead, I made a 50 megahertz transmitter. So I needed to neutralize my final amplifier stage. Was somebody gonna say something? So the answer is to eliminate self-oscillations. If you remember Dan and his first attempts to make an amplifier, remember that you need to neutralize your final amplifier. So here's pictures of a amplifier that's trying to break into oscillation. And here it's showing us. Go ahead.
You're basically neutering it.
Yeah, exactly. You're keeping it on a leash, keeping your wild animal or your wild beast on a leash. And a lot of it has to do with limiting the maximum frequency that the amplifier will work at. In my case, I had an auto amplifier, it was just many, many times lower frequency than what it turned out to be. And so all I needed was some capacitors that would just feed that energy back, and it would have stopped. So here we change subjects again into a different type of modulation. We started out talking about amplitude modulation and then sideband oscillation, single sideband. Well, here's something completely different. So we talked about you could impart information by changing the amplitude, but shifting the whole thing 90 degrees, you can impart information by changing the frequency. And this is for us, for technicians, this is the most common mode that we use is frequency modulation, because our handy talkies and radios that we use to talk through repeaters are all FM. And so in this case, we're changing the frequency. So here's our audio signal, and here's our carrier. So our, maybe 146 megahertz carrier at our 1000 hertz audio. And instead of changing the amplitude, you see the amplitude, this would be AM. So we could see the amplitude is going up and down in proportion to this amplitude. But with the FM, the frequency is changing with the amplitude. That has, let's see what this says. Oh, okay. So they don't ask you, let's see what they ask you. What is the name of the process that changes the instantaneous frequency of an FM wave? And that's frequency modulation. So again, the question is asking about frequency of the RF wave. And frequency is so they're talking about changing the instantaneous frequency of the RF wave. All of the answers start with frequency, but only the correct answer is frequency modulation. Frequency modulation has a lot of advantages and disadvantages. We always associated it before we were hams with FM with broadcast radio that gives us the nice clean signal to listen to music to versus the AM, which is noisy. And that is just one aspect. The advantage of FM is because the idea is that this amplitude doesn't matter anymore. And noise tends to be amplitude modulated. And so if there's noise on this signal, it's just ignored because we're only caring about the frequency. And it's pretty hard to create noise that is frequency modulated. Unfortunately, not hard enough, as I found recently with some items in the house that are creating interference on in my FM radio, but it's harder. And certainly atmospheric sources are generally not going to be frequency modulated. So we start here to talk about the method of making FM in a transmitter. So we need something called a multiplier, which generates the harmonics so we can get the correct frequency. So the question is that what is the stage of a FM transmitter that generates a harmonic of a lower frequency? So if you think that we're mixing two signals together, the term multiplier will jump out at you. Although mixer will be there too, and that's not a bad answer, but it's wrong. It's multiplier. So there we're talking about FM phone transmission of 60 kilohertz being the bandwidth, and 16 kilohertz is the correct answer. So if you have your basic deviation of FM, because remember we're talking about changing the frequency, so we're talking about deviations in frequency now. So we have a 5 kilohertz deviation with a 3 kilohertz modulation frequency. 3 kilohertz equates to the audio band pass of 300 to 3 kilohertz that we typically use for radio work. It's certainly not the entire bandwidth of our speech. So you've got 5 kilohertz plus or minus 5, it's 10 plus or minus 3, which is 16. So there is an answer which is 8 kilohertz. So don't just add the two together. You have to add the two together and double it. Oh. And here they show that bit of math there. So the next one is, what is the frequency deviation of a 12 megahertz reactance modulated oscillator? So this is kind of devious because there's other questions about reactance modulation, but in all practical purposes, reactance modulation and FM are the same thing. So they're kind of being a little cagey here with their question. So we could say a 400 kilohertz, a 400 hertz deviation of a 12 megahertz reactance modulated oscillator and a 5 kilohertz deviation. So what the question is that they've got 12 megahertz and 5 kilohertz deviation. What will be the frequency deviation? So do they show the math here? Okay. Yeah, I'm reading this and trying to give you anything more than what they give you here in the book. And I think your best bet is going to be just to memorize that 416.7 is the answer should you get this question. So yeah, I'm sorry I don't have more to give you than that. They're showing you here that, you know, the 146.52 divided by 12. Yeah, I'm sorry. Just memorize the answer. Why are they showing us the space station? Okay. So here they get into phase modulation. So FM and phase modulation are similar things. And a reactance modulator is something that is used to create the FM or phase modulation. So if you really thought about it, changing the phase angle of a frequency of RF is a lot like changing the frequency. I've had radios where you look at the back of the book and it, you know, gives you all the specifications, and it'll say modulation type, phase modulation. And I just remember that when I looked at that and I thought, wait, I thought it was FM. It turns out it's the same thing. It's just easier, I think, circuit-wise to produce phase modulation than it is frequency modulation. So here the good association is with reactance modulation and produces phase modulation. Here's a basic question about efficiency. Efficiency in general is output divided by input. So 100-watt amplifier that draws 10 amps is, oh yeah, from a 13.8 volts power supply has a efficiency of 70%. So in this question, they're just saying, how is the efficiency of an RF amplifier determined? And I think if you can just remember that it's pretty universally the efficiency is the output divided by the input of anything. And that's what the correct answer says, divide the RF output by the DC input power. You can sort of, sometimes this is useful in the specific answer is useful in thinking, oh, how many amps do I need to supply for my 100-watt amplifier? Generally, we figure, you know, well, this is not a bad, this is not a bad efficiency at all at 70%. We usually just talk about supplying twice the amps needed. Just as a rule of thumb, that would be a efficiency of 50%. So the thing is, what's happening here in this example is that we've got watts here and we've got volts and amps. So we can't do anything with this because these are completely different units of measurement. We need to get this into watts. So, you know, you can't divide apples by oranges. So to get watts, you divide the current drawn by the voltage. And then that'll be the watts, or 138 watts. Okay, so this is a question about okay, sorry, I'm looking ahead to see how close I am to the end. We're kind of running out of time. So this is in the book, shows you quite long calculation for calculating PEP. But let's look at the correct answer is 100 watts. You know, this is actually something that is important, like efficiency in the previous question. This is actually something that's important to understand, unlike some of these other questions. So I hate to gloss over it, but so I hope you look at it, at the explanation in the book. You know, the answer, yeah. So, I mean, I think it's easy to just remember the 100 watts as the answer to this question. And it's not the only question on the test that has asking you about, no, in fact, there's like 4 of them that talks about PEP. So let's continue on. So the thing about here that's kind of not intuitive is they may not explain, well, they probably explain it in the book, but this 0.707 has to do with the fact that, you know, sine wave isn't on all the time. So you've got this, you know, compared to a square wave, you got a square wave would be 100%. Then a sine wave is less than 100% because it's, you know, it's got this area that it's not at full deviation in either direction. And so this is going to have some average time. And it turns out it's 0.7 or 70% or 0.707, or technically it's the square root of 2. So say you had an oscilloscope and you were measuring a sine wave, you could measure, well, okay, the peak is plus or minus 1. Yeah, but what is the you know, the average, or what's called the RMS, root mean square value? and you simply measure that peak by 707, and that's where this comes in down here, is because we're not measuring DC, we're measuring a sine wave, so we have to multiply this first number by 0.707. And then this is the next question here. If you had 625 watts, yeah, so they're saying your oscilloscope measures 500 peak to peak across a 50 ohm load. So you could plug those numbers into this previous equation and then come up with the 625 watts. And there it is. And again, both these answers are kind of rounded off. It's a similar question, but doesn't have the math in it. What's the ratio of a peak envelope power to average for an unmodulated? So the thing is here is the key thing is that it's unmodulated. So the peak and the average are the same thing. So it's 1. So again, the ratio is the ratio still is 1. Now this next one, they're saying it's the same question. What is the output of an unmodulated carrier? So both of these questions are the same thing, that if you have an unmodulated carrier, the peak envelope power is going to be just the power. So a steady state carrier is both peak power and average power. Oh, they were back to decibels. You remember decibels from the technician class? And everybody went on to study them mightily? No, okay. This is basically the same question that was on the technician class. What dB change represents a factor increase or decrease in power, a factor of 2 power, and that just is 3 dB. You can look at these graphs. There's 3 dB. Power 1 over power 2 ratio being 2, so say it's 100 over. You went from 50 watts to 100 watts. A change of 2, well, that would be an increase of only 3 dB. And which is interesting because this is on the receive side when we start talking about signal strength, but this is useful and not a question, I don't think. No, it is a question. Okay, cool. Going from S1 to S2, you can see is 6 dB, which is, in this case, we're dealing in voltage, so we're doubling the voltage and getting a 6 dB change. So, putting it another way, just one S unit increase, the power of the transmitter, that's the power of the distant transmitter, not your transmitter. Well, for the far end station to hear a difference in your signal of 1 S unit, you have to increase your transmitter 4 times. So an S unit is 6 dB. 6 dB is a 4 times change. Yeah, and here they show it. So they're showing here an S meter, and the thing about decibels is, I think, is, at least it's easy for me to remember, is that, well, 0 is 0, 10 is 10, 20 dB is 100, and 40 dB is 1,000. So if we're saying we're 20 dB over this S9, so this distance here is actually 100 times difference. So this scale is linear in dB until we start getting into these higher levels. Because remember, we said that 8 to 10 S units is 6 dB, but here we're starting to talk in terms of 20 dB. Okay, changing the subject again. Again, to the more esoteric, Class C amplifiers. So amplifiers are defined in their design by class units. Let's see, okay. So in this case, they're asking the question about which amplifier has the highest efficiency, and in this case, it's Class C. And of all of the questions, answers here, C is the highest. They tend to, for this example, they tend to be more efficient as the letter increases. And we only thing that this graph I think is useful to communicate is a Class A amplifier is the least efficient, but produces the most faithful reproduction. So like if you were designing a microphone amplifier for your microphone into your transmitter, you would probably be designing almost certainly for a Class A amplifier. So I don't think they, yeah, I think this is the only question. There's two questions about Class C, and the first one, I'm sorry, I missed it. Class C amplifier is not linear. So the idea is that it is appropriate for amplifying an FM modulated signal because, as I said before, the amplitude purity isn't as important as you would need for an amplitude modulated signal. Okay, here we go. Lowest distortion, highest efficiency. Picture of a linear transmitter, I assume, to let you know that that transmitter probably needs to be a Class A or AB to be efficient. I mean, to preserve the purity of the signal at the expense of efficiency. Okay, so we've got a question that has to do with vacuum tubes. Vacuum tube RF amplifiers. Oh, and we're almost at the end. Oh, wait, this is the last question, all right. So probably none of us will ever be touching a vacuum tube RF amplifier, but if you ever do, you need to adjust the maximum power output without exceeding the plate voltage. So used to be that you'd select a frequency and then you'd have to tune your vacuum tube transmitter parts, the amplifiers, the parts that's actually producing the majority of the transmitter power, and you would do that by looking for a dip. So the answer, yeah. So again, if you get if you get a question that asks you about vacuum tubes adjustment, just remember dip. They pronounce dip as the answer. You can read the explanation, but again, this is just not something you really need to know unless you're, somebody gives you a kilowatt vacuum tube power amplifier, thank them profusely and then study up on how to adjust it.
Actually, I have a 520 Kenwood that I received in the finals are tubes.
Right.
And one of the things that they told me to do was to make sure I transmit to a dummy load so that I do this, I set the tubes to the right frequency.
Yes, so that's a very good point, is that, again, I say it used to be, you actually you needed to start transmitting at a low power into a dummy load and to get everything set up, and then you could actually transmit into your antenna.
That's because that the device has been hasn't been used for 40 years. So in order to get the tubes back in alignment and stuff, that's what they said to do.
Yeah, but that, it's one of those things where you could remember that, oh, at this frequency, I need to set it to this setting. It's not that something you have to precisely set every time, but it is a setting you need that needs to do. And there was a period of time, and there's still these transmitters still being used today, where they're called hybrid. So you'd have a conventionally looking transceiver, but the final amplifier tube would be a vacuum tube. Because, vacuum tubes, turns out they're really good for transmitter finals. It's only been a relatively short a time where we've even had transistor outputs that could produce 100 watts. And at the beginning, they were just very fragile. If they saw too much SWR, they'd blow up on you, whereas the vacuum tubes are extremely rugged. So, are there any questions? Is everybody asleep?
Guess everybody's feeling a little overwhelmed and her brain is full.
Yeah, I'm so sorry. This is
It's
This
just a lot
is-
of
this is
esoterica to absorb.
it is. I mean, this to me is like sitting in on an anatomy class or something, and then coming back the next week and trying to remember all of the names of all the tendons in your hand or something. It's like, well, it's interesting, but am I gonna need? Yeah, Bruce says mind numbing. I'm sorry, it is.
Well, remember, you don't have to get 100% on the test.
Yeah.
It's okay to miss a few questions. And also remember, it is multiple choice. And so if you come to a question where you just completely don't remember, you can always try to eliminate one or two of the choices that seem useless. And if that doesn't work, just take a stab and guess and go on to the next question.
Yeah, and unfortunately, on the general test, there are less dumb answers.
Yeah, but fortunately, all
But-
these folks are smarter about radio than they were a couple of years ago when they first got into it. So,
Yeah.
they go together.
And I've hopefully given you some, like I said, associations. If they, like I said in the last one, if you see an answer about tuning a grid dip, or tuning a vacuum tube amplifier, and the question, there's an answer about grid dip. It's like, okay, well, I don't understand what that is, but I remember that was that's the answer.
It makes a world of difference to actually see this stuff in action.
Yeah. Yep.
See the meters and the components. Otherwise, it's just a bunch of word salad.
Well, and I wish the questions were more pertinent. It's like I told you about, being able to calculate the peak envelope power. You may never have to do it, but that has an actual application, or calculating the efficiency. That has a real world application where, like I said, some of the stuff I doubt if, unless you really want to get into designing amplifiers, you'll answer the question right. You'll walk up and turn your test in and you'll never think about it again. Lisa? Oh, go ahead.
Go ahead.
I thought Lisa had her hand up. Nope. Okay.
I have a question, if you don't mind.
Yeah.
This is back about the skywave propagation and what have you. And one of your diagrams talked about the critical angle of your coming out of your antenna.
Mhm.
And I understand the 1,200 miles and the 2,500 miles. That's to get the greatest distance. But do we use different antennas or rotations or alignments or whatever to try to raise that angle up so that you can talk to the guy 1,000 miles away instead of the guy that's 2,500 miles away or whatever?
Yeah, that is a completely reasonable question, because what we can do is try to keep our keeping the angle as low as possible. So, and that, let's put it this way. Okay, say you take a simple dipole on a HF frequency, the distance that you put it mounted above the ground is going to affect the angle that the energy will leave it. If you put it really close to the ground, the signal will go straight up. And some of it will actually bounce back down. They don't talk about that in the thing. Most of the energy will just get absorbed, but some of it will come back down in a roughly cone shape about, 2,200 miles, I'm sorry.
500 miles.
Yeah. That's typically, though, not what we want to do.
Right.
It's typically a very bad idea, but sometimes it's exactly what we want to do. If you want to take to Sacramento, that's a very good way to do it. Otherwise, as you raise the antenna off the earth, the angle will start to, at some point at about a half wavelength above the earth, will reach an optimal angle where the energy is kind of in the Goldilocks spot of coming off the antenna, not too high, not too low, but just pretty much straight out, so that it will hit the ionosphere at that correct angle. So yeah, I mean, and that whole thing is a big calculation. It includes the ground. It actually it has to do with the type of ground. How much, is it rock? Is it sand?
Well, all I was looking at is, I understand maximizing it to get the farthest, but and I'm not going to go out back and raise or lower my 80 meter antenna by 10 or 20 feet or something let's see if I can talk shorter or longer or whatever. I mean, I understand that.
And nobody does that. Nobody does that.
No, I wouldn't think so.
You'd put it out a half wavelength if you can.
Okay.
And that's it.
Yeah, so Jack, what you would do if you're interested in contacts over a different distance is you would probably switch to a different frequency band.
Sure. I understand that too. It's just part of the setting up an antenna, and maybe multiple antennas certainly, and just trying to optimize it. Yeah.
Generally, with HF antennas, you do the best you can to get the angle of radiation as low as you can get it. And particularly on the lower frequencies, 160 meters, 80 meters, you can't get the antenna high enough no matter what you do.
Unless you got a eucalyptus tree in the backyard, right? No, just kidding.
Just put your 160 meter antenna at a half wavelength, which would be 80 meters above the ground.
That's exactly right.
Okay.
Well, you guys are hanging in there pretty good. Does anyone have any general comments about the class, or how is it going for you, or there's something we could do to make it better?
Perhaps next time around, can you guys hear me?
Yeah,
Yep.
I'm hearing you.
Okay, my square isn't lighting up like it should. Perhaps next time this could be a 10-week class instead of a 6-week class. I'm serious. It just takes me so long to break this down and absorb it. And it's like I can either do that or I can try to memorize the answer to 465, however many
Yeah.
questions. And
Our,
it's just a
our,
lot to deal with it in 6 weeks.
It is. It's hard to get the pacing right. A longer class, I'm sure, would be better for some people. But we're sticking with 6 weeks. Sorry.
I think for most of this, you got to just train your brain to go to the right answer. Just
Yeah.
study it and just get used to recognizing what the right answer is. Figure it out later.
And I gotta tell you, for some reason, and I think when I took the general test, it was easier than it is now. But I found the general extremely easy. Oh, bye, Roxanne. But I found the extra tests, some parts of it extremely hard. And that's exactly what I did was I just kept taking the test over and over and over again until I was just visually associating the correct answer with the question. There's parts of the extra tests that I didn't care about. I still don't care about. I just wanted to get the right answer. And so, don't feel bad about looking at these answers and going, or these questions and going, how the hell is that ever going to be useful to me? Because it may not. So yeah, like I said, use those different programs. There's free ones. I used a free one that I was just, again, by just rote memorization, just visually associating the visual of the end of the answer with the question. Not even on a level of reading it. It was just like associating those two things in my mind from just doing it over and over and over again. I probably barely passed too.
For what it's worth, there's a phone app called HRE General. I would recommend that to anybody who is a phone enthusiast. I've also got my written flashcards, so there's 2 different modes to try to get it into your brain, if that's of any help to anybody.
You
think the
can
more the better.
also, you can take QRZ offers a lot of tests and they'll tell you what you get wrong. You can take it over and over and over again, which I have started to do.
Yeah.
So
Yeah, that's what I just did.
Yeah, the reason I went with the app is because I can just pull my phone out of my pocket anywhere, anytime I'm waiting, as opposed to having to come home and sit in front of, dedicate time to sit in front of my computer.
Yeah.
A few minutes here, a few minutes there. Hopefully it will all add up to a passing grade.
When I took the general, we didn't have phones.
Well,
the first time I studied for this stuff, we were still using vacuum tubes, and the stuff we have now is like pie in the sky.
Yeah, actually,
Grids and control grids, and anodes and cathodes, and
yeah, it used to be if you'll go far enough back, they would give you a blank sheet of paper and say, draw a Colpitts oscillator. It wouldn't even be multiple choice. It'll be like, draw a schematic for an oscillator and the correct one too. So some parts of this is easier, but I think there was a time when more people built their own equipment, and so understanding what a Colpitts oscillator was from a Hartley oscillator mattered.
on wheels. They were big things.
Well, just stick with it. This does get more familiar as you spend time with it, and that will certainly help.
Yeah.
Next week, we'll be talking about radio transmitters and radio
Receivers.
receivers rather. And our guest speaker will be Don Taylor, K6GHA, who will talk about radio sport and contests. He's a big proponent of radio contests. It's a whole different way to have fun with radio. And I think you'll find his enthusiasm is impressive. Anyway, thanks for sticking with it. We're halfway through. You guys, if you keep at it, you guys will pass the test and you will get your general license. That's absolutely what's going to happen. So we will see you all next week. Meanwhile, if anything's puzzling, email one of us or email several of us and compare our answers.
Dad.
And pick the one we like the best, right?
That's right.
Yeah.
All right. We will see you all next Monday.
All right.
Thank
Bye-bye.
you, everybody.
Bye.
Bye.
Thanks.
Thank you.